hyperbolas. We're going to build on the information we learned about the other two conics. We've still got parabolas to go, but this will be the third in our set of four. We've got vertices, more than one, foci, more than one, and here's something new, asymptotes. We'll be using the technique of completing the square. Actually, I don't think we'll be doing this one. It won't be tested on this. It's something we can talk about in class, though, if you are interested, of course. We'll do a little review here of what we just learned about ellipses in the last lesson. We notice that nothing is being added or subtracted from this x before we square it, nor from this y before we square it. This tells us that our center is 0, 0. And what are we being told down here? Do you remember? This represents a square, and this represents b squared. I know this is my horizontal axis because it's the larger one and it's under x. So this would be 7 squared. This one is 4 squared. So if I think about how this lays out on the grid, I've got 7 away horizontally to find my vertices, 4 away vertically to find my other vertices, or sometimes referred to as co-vertices, and my center, of course, right here. So if I were to draw my ellipse, I guess this is not a very good drawing, but you get the point. What are my coordinates of this vertex? It's -7 and 0. Looking at less 7 from your x coordinate and making no change on your y coordinate. And this one will be a +7 and 0. This coordinate right, or this point right here, will be 0, 4, and this one will be 0 and -4. Gets a little more complicated when I start looking at something like this. This actually has something being subtracted within the squaring. That tells me a lot about where the center is. My center right here is at 2, 5. This is the same as 10 squared, and this is the same as 3 squared. So my vertices, I'm going to subtract 10 from this. I'll have -8, and I haven't gone up or down on my y, 5. This one, I'm going to add 10, that'll make it 12, 5. Here, I'm going to add 5 to my y and subtract. Did I say add 5? Oh, add 3 to my y and subtract 3. So I could put this on a coordinate plane, couldn't I? Looks like this. And if I were going to put it on the coordinate plane, let me draw that in afterward. I think it's a little easier when you draw it in afterward. I know I have to go over 2, so right about here, for where my y-axis is. There's my y-axis. And I have to go up 5, so that puts my x-axis right about here. It's really easier to put these on a coordinate plane after you've figured out their shape from the center. Okay, we're introducing ourselves to the hyperbola. Here's that standard form. We see that A and C are associated with x squared and y squared. So the multipliers on x squared and y squared, if those are exactly the same, we know we have a circle. When they are not the same, but they have the same sign, we know we have an ellipse. Whether they are the same or not, if they have a different sign, we know we have a hyperbola. Here we're looking at one. Let's look at all the components. The main thing we see is that we've got a discontinuous graph here. We've got one branch over there, and we've got another branch over here. The other thing, which isn't shown here, but we'll talk about it in a moment, the focus, instead of being on the inner part, it is going to land right here, sort of on the outer reaches, away from the center. The center we see right here. We have 2 vertices, and they remind us really of the vertex on a parabola, don't they? And the axis which goes through them, both of them, in a parabola it's called the axis of symmetry. Here it's called the transverse axis. And in order to keep that in mind, remember it traverses between the 2 vertices. Transverse. There's another axis, and it may be difficult at first to understand why we even bother with it. It's called the conjugate axis. What it does for us is it helps us draw this, you notice this box we've got? Here I'm just going to mark the corners. This box allows us to draw accurately the asymptotes, and that's the main reason we figure out what it is when we're doing the sketch of a graph. Where we get our numbers from, I'm going to show you in a few minutes. But all those matter, as well as this is what told us that we had a hyperbola. The vertices and the foci, as we see, lie on the transverse axis. We just talked about that. We want to transform this equation, what we're looking at right here, to expose the lengths of the transverse and conjugate axes. What we're going to do with this is we want the right member, which is here, or the right side, to equal 1. And we want the coefficients of the numerators, all the terms in the left member, to also equal 1. They're a long ways from that right now. So let's work on it for a minute. If I want this to equal 1, I've got 2. Let's write out the equation up here. If that's going to equal 1, I've got to divide everything by 144. Now you may have noticed, and this is often the case at least in these student versions of a hyperbola, that if we were to multiply 9 times 16, maybe doing it in your head right now, we would get 144. I'm going to put that thought aside for a moment. So we've done this. Now we want to do this. This has a 9 in it. What do we need to do then? We're going to multiply this by 1/9, and whatever I do there, I've got to do here, right? What have I got here? Just a fancy 1. Doesn't change the value of my fraction at all. Over here you saw me put parentheses around that 16y squared because I'm going to multiply that by 1/16, which again is just a fancy 1. And I will end up with this canceling out to 1, this canceling out to 1. I'll have x squared over, when I divide 9 into 144, I get 16. And I'm going to subtract. When I divide 144 by 16, I get 9. Okay, so I have transformed the equation. And how has that exposed the lengths of the transverse and the conjugate axes? Very much like it did, in fact, exactly like it did with the ellipse. This is the same as 4 squared. This is the same as 3 squared. And please notice my x from the center, 1, 2, 3, 4, and my y from the center, 1, 2, 3. What determines the shape of the parabola? It's these semi-axes that determine the shape. Or, to get more primary about it, it's the asymptotes that determine the shape. The asymptotes. And we know where the asymptotes are by knowing what is the length of my conjugate axis and what is the length of my transverse axis. How would you describe the hyperbola for which the difference constant is 0? Well, we haven't even talked about that difference constant yet. We'll talk about that in just a moment. Here's the one we were working on, the positive term right here. We have a 4. That's the semi-axis, the transverse semi-axis. The 3 determines the conjugate axis, and to be specific, the semi-conjugate axis, or half of it. There's another thing we have to pay attention to. We'll do it in just a moment. You'll notice that the transverse axis is horizontal here. This sign, this one has a positive on it, and this one has a negative on it. This determines which is the transverse axis. It determines whether the vertices lie right here or here. Let's do this one. Now this looks pretty familiar to us. It's got some of the same numbers. Do you remember what our steps were? First, we wanted to have the right member, see if I can write small here, be equal to 1. And then we worked on the coefficients on the left, all those squared terms. We wanted those coefficients to be equal to 1. Well, that's not the case here. We actually have the right member equal to 0. Well, let's correct that immediately by subtracting 144 from both sides. Now we want it to be equal to 1. We don't want it to be equal to -1. So this time we're actually going to divide by a negative number in order to get that right member to be positive. Okay, so that's now equal to 1. What else did we want to happen? We wanted these left coefficients to equal 1, and right now it equals 9. So we can fix that. We say this is x squared divided by a negative 144 divided by 9, negative 16. And this will become a positive y squared divided by 9. Ooh. Let me just move this up here. We have something a little different. Only a little different, but it makes a big difference. Our negative is now on x and our positive is on y. This changed things. Now our vertices and our transverse axis, is now up and down. Whichever one has the positive, that's the one that's up and down. Does the transformed equation explain the change in the orientation? It sure does. When the x term is positive, as it is here, the transverse axis is horizontal. When the y term is positive, now in this one, notice I've led with the positive term. That's a pretty conventional way to do it. When the y term is positive, the transverse axis is vertical. These are referred to as conjugate hyperbolas. Perhaps you can see why. Can you see why? The only difference between them are the signs, right? This is y squared over 9. This is y squared over 9. This is x squared over 16. This is x squared over 16. This is all equal to 1. Yeah. The only difference is right here. Positive x squared minus y squared. Positive y squared minus x squared. Conjugate. We've seen that word a lot this year. Now we're going to use geometry. Remember we talked earlier about locus? Here it is again. We know for a circle we can define that in terms of the locus of its points, a geometric definition. A circle is the set of all points equidistant from a fixed point, that fixed point being the center of the circle. Now, an ellipse, its locus is the set of all points for which the distances from two fixed points sum to a constant. And what were those two fixed points? The foci. And if you think about it, the center of a circle, it's really a focus, isn't it? Now we're going to define the hyperbola in terms of locus. It's the set of all points for which the difference, that's why you have to have different signs here, for which the difference between the distances from two fixed points, and guess what those are going to be, is a constant. There's a certain symmetry about all of this, isn't there? We see a pattern developing in conics and how we define them, at least geometrically. So we're going to look here at a hyperbola and see if we can make sense of this little geometric definition. The set of all points for which the difference between the distances from two fixed points, we knew these were going to be the focal points. So a set of all points. So we just start with looking at one point on a hyperbola. We could have chosen any point here, any of these points on either branch, and it would still be true what we're saying here, that the difference between the distances from this focal point and this focal point is going to be unchanging. In this case, for this point, the longer distance, d1, minus the shorter distance, equals some constant number. If, let me change colors. Go to purple. If I had chosen, let's say this point, again we've got x, y. And if I had looked at these, here is the distance from the first focal point. I'll call it, what do I call it? D3, just because I don't want to get us confused here. This is the shorter one. and the longer one will be this one here. Call that D4. And so the longer one minus the shorter one is going to be equal to that. So we could say that D1 minus D2 is equal to D4 minus D3, and I could go on, for the rest of my life finding points here. But you don't have the rest of your life to spend watching me do that. Okay, the major semi-axis is the distance A. The minor semi-axis is the distance B. Now, I don't think I should have said major. I think I should have said transverse. And minor shouldn't be called minor, it should be the conjugate axis, right? Now I've got it correct. And the focal radius, if you think about right here, I'm making a circle around the center, is C. This is different from what we've seen before. C is longer than A. The difference between the distances to any point, D1 minus D2, if we take the absolute value of that, it's equal to the full length of the transverse axis. So let me write that out. Length of transverse. Oh, let's go back a moment. So this right here, our K, the constant, what is that constant? That's right, it's the length of the transverse axis, which is the distance between the vertices. This little formula here is something we're going to use when we have to identify exactly where the focal point is. We'll get to that in a minute. Oh, I wish I hadn't done this. I have to keep fixing it. Okay, maybe that actually will help us remember. I like to think that mistakes are there for a reason. That's the transverse, and this is the conjugate. Would that do it? You know what that is, right? Conjugate. Find the vertices, foci, and asymptotes, and then draw the graph of this hyperbola. Well, this is easy enough to do, right? I know my A is 4, and my B is 3. I know that my transverse axis is horizontal because this is positive. I also know that my center is at 0, 0. So let me draw it. We're going to do things differently when we do a hyperbola because we're going to draw asymptotes before we try to draw the actual shape on our coordinate plane. My A is 4, so I'm going to go to here, 4, and to here, 4 away. And then I'm going to be interested in a box. I just really want the corners of this box, and you know why. I want to draw those asymptotes. The other thing I might be interested in is where my focus is. Did I not write that down? Oh, okay. Let's go back a moment. C squared equals A squared plus B squared. That's pretty straightforward. I think I can remember that. So C squared is going to equal A squared, which is 16, plus B squared, which is 9. So my C is equal to 5. I know my focus is going to be right there and right there. And of course I just put it on the line of the transverse axis. Now I'm going to draw my asymptotes. Ugh, those could be tricky to draw. You will use a ruler. I am, of course, going to demonstrate what you shouldn't do. And let's try to draw it without a ruler. All right. I thought teachers were supposed to model the correct way to do things. All right, that's about as good as I can get it. Now, we're actually going to draw it. It was good that I put the focal point in because it reminds me of where this is supposed to go. Because the hyperbola will always go around, it swings around that focal point. Otherwise, I might be inclined to draw it in the wrong place. I do know that my vertex for my hyperbola is lying right there. So let me draw it, and I'm going to get ever closer to my asymptote. That's what an asymptote does, right? You get closer and closer. Apologize for my poor drawing, but you get the idea. Because you're smart. There. So that's how we draw it. Here's the general equation. Woo! It looks terrible, doesn't it? I use A here, and I think your book does too, for the transverse axis. The R sub x is something you may see in your next course. It talks about the radius sub x, the radius sub y. That doesn't change even when the transverse does. But now we have the conjugate axis here because it's negative. Conjugate axis, the transverse axis rather, here because it's positive. We like this one better because it looks simpler. I'm going to abort right here. Well, I shouldn't say abort. I'm going to stop right here, and we'll get back to this. We'll do a second session on this because I'm already over a half hour. I think that's long enough.